ch14, chapter 14, the basic elements and phasors. We're going to talk about the frequency response of basic R, L, and C elements. That's a resistor, an inductor, and a capacitor to sinusoidal voltage or current. So the sinusoids we're going to start with are going to be represented by a lowercase letter, I for current and V for voltage. And then they have a maximum value, just like a regular sinusoid. This is the amplitude. So Im would be the amplitude of the current sinusoid waveform in amps, and Vm would be the amplitude of the voltage sinusoid waveform in volts. Omega is equal to 2 times pi times f, or that is the angular velocity in radians per second. And f is the frequency in cycles per second or hertz. And then again, I is the AC current waveform and V is the AC voltage waveform. This is an example of a voltage waveform and a current waveform. The voltage is the one in black, and then the current is the one in blue. And it's showing you the maximum value of each one. That's the amplitude. And it's also showing you for a resistor, those two, the current and the voltage, are in phase, which means that their zero crossings are the same and they're at the same frequency. They're not shifted to the left or to the right from each other. So that being the case, it's just straight up Ohm's law when you want to calculate when you have a pure resistive element involved with the voltage and the current. So V equals IR, V sub M equals I sub M times R, or I sub M equals V sub M divided by R, where R, again, is the resistance in ohms. With an inductor, V sub L is going to be omega sub L times the current, the max current, would it be this current here, Im. So the voltage across the inductor in volts is equal to omega times L, omega being the angular velocity, L being the inductance in henries, times I sub M sine of omega t plus 90 degrees. So there's a 90 degrees phase shift in the current with the inductor. XL is a variable. It's the inductive reactance in ohms, and it's equal to omega times L, or Vm divided by Im, the two max values of the sinusoids. And then you can remanipulate this until Vm equals I sub M times XL. So here's an example of the current flowing through an inductor. This is a sinusoidal current, and then the resulting voltage leads the current by 90 degrees. So you get this V sub L leads I sub L by 90 degrees. So when you have this, that plus 90 means it leads by 90 degrees. If you have a purely capacitive element, I sub C equals 1 divided by omega C, where omega again is the angular velocity in radians per second, C is the capacitance in farads, times V sub N times the sine of omega t minus 90. X sub C is the capacitive reactance in ohms. It's equal to 1 divided by omega C, also equals V sub M divided by I sub M, and then V sub M equals I sub M times X sub C. So the reactances are a translation of these two elements, like the resistances that you're all familiar with. So we just use X for the variable for reactance. So here's a purely capacitive element, I sub c going through it, v sub c across it, where v sub c equals Vm times sine of omega t. And you could see that the current leads the voltage across the element by 90. So in an inductor, the voltage leads the current by 90, and in a capacitor, the current leads the voltage by 90. So you could say leading because it's coming before it in time. This is the time axis right here, this omega t axis, with time t being the independent variable. So the current's coming first, which means it leads it. Up here, the voltage is coming first, which means it leads the current. You could also say here that the voltage lags the current by 90. And up here, you could say the current lags the voltage by 90. Okay. It's all dependent. Normally we say what the current does, not the voltage. So this is probably the more correct way to say it. The current of a capacitive element leads the voltage across the element by 90, and then here it would be more correct to say for the inductor that the current lags the voltage by 90 degrees. So on to the next section, the frequency response of the basic element. The resistor R just equals R. Frequency has zero effect on impedance, okay? We're looking at a term called impedance. The impedance is going to be a combination of resistance and reactance. Sometimes the reactance might be zero, and sometimes the resistance might be zero, but the total impedance involves both of these. With the inductor, the impedance is just reactance, and it's equal to X sub L equals omega times L, which is equal to 2 pi F times L. So you always need a frequency to be given to be able to calculate the impedance, and this is how you calculate it. Sometimes you're given a frequency in hertz, sometimes you're given a frequency in radians per second. With a capacitor, X sub C equals 1 divided by the quantity omega times C, which equals 1 divided by the quantity 2 pi F times C. So as you can see, when F is a high frequency, you have a high reactance here. As F goes up, the X sub L goes up. When F goes up in this equation, X sub C goes down. So for very high frequencies, this number becomes large, the number in the denominator becomes large, and then X sub C becomes small.